Hello everyone and welcome back. So now we're going to learn how we actually calculate that first moment of area Q. First moment of area Q. So what is it? What do we need it? Well, we need it for all of our equations so far to calculate those shear stresses. However, this is honestly one of the more difficult aspects when it comes to these kind of problems. It doesn't have to be difficult though. There's actually some very simple ways to do it, especially when you have nice shapes like this. Now, why is it difficult? Well, when you're calculating Q, it's a different value depending on what point you're going for. So all three of those values would have different values of Q. And so when you're having to do a problem like this, you're going to have to calculate Q multiple times. So let's come up with a good way of doing it. So first off, how do you choose the area? Because if you remember, Q is equal to that integral y dA, okay? Integral y dA. Or in most cases, that's just going to be the y times the area, where that's the distance to the centroid. So how do you choose it though? Because I could go from the bottom or from the top. I just have to go all the area from the top of the member down to my point, or from the bottom of the member up to my point. One or the other. So in this case, it doesn't really matter because this is more or less along the midline. And so I simply have to find, the area that's above it. But I usually say whichever side is closest, choose that area. You can do either one, but just choose the one that's closest. However, if you choose the opposite, you will get the same exact answer. So now with that in mind, we can calculate Q by finding the distance from our neutral axis to the centroid of this area. Okay, not the big rectangle right here, just the centroid of this shape. Just the centroid of this shape right here. So it would look something like this. We have our distance from the neutral axis to the centroid of my area times the area of that section. Now, that was difficult though, and I hate difficult things, so let's make it a bit easier. Because if we want to, rather than calculate the centroid for that strange shape, you can make it out of a bunch of simple shapes. So in this case, I'll just have 3 rectangles. And I'll get the same answer. So just like before, I want that centroid of this overall shape times that overall area. But I can also break that up, because the centroid would be simply this right here. That's each of those individual areas times their particular centroid. And then I divide that by the total area, which if you look right here, since I'm multiplying by the total area, the bottom and the second multiplication area cancels, and I'm just left with these 3 right here, which makes it so simple. You can more or less just calculate Q for each individual shape and then add them all together. This is the best way. Make a table. We've done tables so many times for other things, and you'll have an absolutely wonderful time with it. Okay, so let's finish up this section and talk about shear stress and beams with rectangular cross sections. Now there is a derivation for this. However, the biggest thing I want to give you is simply that for a rectangular cross section, the maximum shear stress occurs at the centroid of that cross section, and it's going to be equal to our equation right here. So if I plug it in, what I can find out then is that it's going to be equal to 3 times our internal shear force over the area. And that's just coming from how we're calculating everything, how we're calculating Q and the moment of inertia. Everything cancels out to be very, very nice. Oh, so we're in an example. But thank you for listening. I hope this helps you, and I'll see you all next time. Bye-bye.